Let's just wait for him. Okay. Now we want to continue our discussion about vectors. So let me start with the example to refresh your memory a little bit. So example. I give you a figure here. So you have an equilateral triangle here, and another one exactly on the same line with the same size, exactly identical equilateral triangles. So we have this point A, this point E, B, and C, and D. And then we have a vector here. We call it Q. We have another vector here. We call it small p, actually. And we have another vector here. We call it R. Just refreshing your memory. This is a very simple example. So I have two identical equilateral triangles lying on the same line. And then I have given you these vectors on this figure. And then I was asking you which one is true. So number one, we have EB equals to R. Number two, we have the magnitude of P is equal to magnitude of Q, or the size or the length. Yes, do you remember that was the notation that we used for the length? Number three, BC, the vector BC is equal to R. Number four, DB is equal to Q. Number five, ED is equal to P. And finally, vector P is equal to vector Q. So we want to see which one is true, which one is false. So you remember that two vectors are, so what was a vector, do you remember? What was a vector? Yes?
Like a line in a certain direction.
Yeah, so it's a line segment with a particular direction, yes? So that is the vector that we had. And then, do you remember when two vectors are equal? Yes?
Same length and direction.
Yeah, being parallel, same length and the same direction. Yes, that's the meaning of two vectors to be equal. So this picture we have, and then we are claiming that vector EB is equal to vector R. Okay, so vector EB, so it's very important to respect the order of these letters, yes? So E starts in the beginning, B, so this is the initial point of my vector, and this is the final point, and then you know that the tip of the arrow should be at the final point, yes? So EB, it's not actually shown in the picture, but you know that when I talk about vector EB, I need to start from B and end here. So this I need to do it myself. So do you think that this vector EB is equal to vector R?
Yes.
Yes, because they have the same length, because I told you that they are identical copies of the same equilateral triangle. So the length are all the same here and there, and also these are the length of the sides here and the length of the sides here are the same. So it means that this vector and that vector have the same lengths, and they are parallel. Why? Why they are parallel? There is a theorem before that. So you see, these two lines are parallel. So we don't know they are parallel, but we know that this transversal line, this angle is 60, this angle is also 60. Yes, this angle is 60, this angle is also 60. So I don't know these two lines are parallel, but I know that these acute angles making, that these lines make with this same line are actually both equal to 60 degrees. So then I can conclude that these two lines are parallel. Yeah, so if you want to be strict, so these two lines are parallel. Okay? So these two lines are parallel. They have the same lengths, and then you see that they have the same, pointing to the same direction. So this one is true, yes? Now, what about this one? The magnitude or the length of vector P is equal to the length of vector Q. What do you think about that? This is vector P, this is vector Q. Do you think that this equality is true or false? It's also true, yes? And then BC is equal to R. Where is BC? BC is from here to here. So this is BC and this is R. Do you think that they are equal? No, even though they have the same length, but they are not equal because they are not parallel. So this is false. What about DB equal to Q? DB is this vector, starting from D to B. Do you think that DB and Q are the same vectors? Yes. They are equal?
No.
No, because even though they have the same lengths, they are parallel again, but one of them is pointing to this direction upward and the other one is pointing downward. So they are not equal because they don't have that property. That's also false. What about ED to be equal to P? So ED is not in the picture, so I need to draw it. So ED is this vector, but D is the final point, so I have to put the tip of the arrow here. Now I am claiming here that ED is equal to P. A is equal to P. Do you think that this claim is true or false? True. It's again true, yes, because you can easily show that this is the same triangle, so that's an identical triangle upside down. So these two are parallel because why? Because this angle is 60, this angle is also 60. You can immediately realize that, and then because these two are 60, then these two are parallel. They have the same sizes, they have the same lengths, and they are pointing to the same direction. So that's also true. What about the other one? False. That's false, because even though they have the same lengths, but they are not parallel, so that's also false. Okay? So that is just a quick refresh of what we have learned so far. So let me just write you a remark here. So what we know is that if someone tells me that a vector A is equal to vector B, I can conclude that this will imply that, of course, A is parallel to B, yes? So this is something what we know. If someone tells me that vector A is equal to vector B, if I want to, I can conclude that these two vectors are parallel. And we can also conclude, let me write this for and, yes, and then I can conclude that the length of A is equal to length of B, but not the other way around, okay? If someone tells me that two vectors are parallel, there is no guarantee that A is equal to B. If someone tells me that the length or the magnitude of vector A is equal to magnitude of vector B, there is no guarantee that vector A is equal to vector B. So you need to differentiate between the size of a vector and the vector itself. Size is one single property of a vector. Okay? So let me give you another example. Assume that someone tells me that vector AB is equal to vector CD. What can be said about the vectors AC and BD? Yes? So someone tells us that two vectors A, B, and CD are equal. So if we want to have a feeling about that, so I have a vector AB, for example, starting at some point, say A, ends at some point B. Yes, assume that this is your vector AB. I have another vector CD, which I know is equal to AB. So what does it mean it is equal to AB? It should be parallel to AB. It should be of the same length, and it should point to the same direction. Yes. So, for example, if I take this one, something like this, yeah, drawing precise pictures are not that easy on the whiteboard, but you understand what I mean. Something like this. So this is vector CD. So I know that vector AB is equal. Is that too big? Yes, a little bit. I think I can clean. So yes. So here I have vector CD. So I know that vector AB is equal to vector CD. I want to conclude something about vector AC, which is this vector now, and vector BD. Yes? So I want to understand the relation between these two blue vectors. So apparently it is clear. If you draw a very precise picture, you can immediately realize what's going on. So can you tell me what is the relation between these two blue vectors?
They're equal.
They are equal again, yes? The reason is that, so if I know that AB is equal to CD, I can conclude that AB is not only parallel, this symbol means parallel, yes? CD, but also the length of AB is equal to the length of CD. If I have a quadrilateral with these two properties, that quadrilateral can be shown to be a parallelogram. Yes? So this implies that ABCD is a parallelogram. Okay? And if that's a parallelogram, it means that the other two sides have the same size and they are parallel as well. So it means that AC is parallel to BD, and the length of AC is also equal to length of BD. And we also know that, we also see that they point to the same direction. So what can I conclude from here? I can conclude that vector AC is equal to vector B. Yes? These are very, very simple examples, but I just want to refresh your memory about what we have so far, and then I just want to give some ideas. Is that clear? Yes?
It says remark there, and then there is a parallel sign. Next to it, there's another parallel sign. No, over it.
This one?
No, over it.
This one?
No, the one over it.
This
yeah,
one?
that one. And also the one next to it. I don't understand the difference between them.
This one and this one?
Yeah.
These are not parallel. This means, if you remember, if I have a vector A, if you measure with your ruler the size of this, say for example, this is 7 centimeters, then this means the length of vector A, which is 7.5 centimeters. So these are not parallel.
These are the. Yeah,
This means that vector A is parallel to vector B. This means the length of the vector that you see inside. This is a symbol. Yes, is that clear now?
Yeah.
Okay, so that's the same thing that I am using here. So this means the magnitude, the size, the length of the vector AC. So if I take the ruler and measure this one, this becomes a number. This represents that number. Yes? Okay. Now let me just teach you something new, which is a very simple one. We want to talk about the opposite or the negative of a vector. So I start with the definition here. This is a very, very simple concept, yes? The negative of a vector A is symbolized by, just as usual, yes, negative A. Because you see that, you know the negative of a number. This is when I am talking about negative of a figure of a shape, I need to define what I mean, yes? Usually if I give you a line and I ask you what is the negative of that line, this is meaningless unless I define it for you, what I mean by negative of a vector. But the symbol that we use is just the normal symbol that we use for negative. But there is a very big difference between -2 and negative vector A. Yes? This negative sign, I am using the same symbol for the negative sign, but there is a big difference between this negative sign and this negative sign. This is the negative of a number, which we learned before, but this is negative of an arrow, I want to teach you what is the meaning of a negative of an arrow, yes? This we need to define. So the negative of a vector A is denoted by this, and it is defined, you see it's defined to be the vector parallel to A and of the same length as A, but in the opposite direction, but pointing to the opposite direction. So you don't need to remember the definition or something. You need to know what is the meaning of a negative of a vector. It's very, very simple. So if I have a vector A, what do I mean by negative of this vector? It is another vector which is parallel to this one with the same size, with the same length, but pointing oppositely. Yes? So for example, if you want to, for example, I can draw a parallel line here, if I can see that they are parallel. And then I will measure this one, for example, from here to here. Yes? This is a line from here to here. This is a line which I try to make it parallel to this one. And I have the same size here, but because A is pointing in that direction, the only thing that I need to remember is to put the tip of the arrow in the opposite direction, okay? And then I can clean the rest of it, which is not necessary. This vector that you see is called negative of vector A. As simple as that. Is that clear? That's the thing that I'm defining, yes?
I don't know if this is a bit picky, but I think we did learn it last time when you talked about multiplying.
Yeah, but be multiplied, there is no number sitting here. But then we will learn that minus A is the same as -1 multiplied by A.
Okay.
Yeah, that's exactly what you said, yes. Okay, is that clear? But even if you want to, there is no necessity to, because I told you before, it's very important to realize there is no location associated with a vector. The vectors doesn't have any locations. So it doesn't matter if you draw the vector here or draw the vector here. That's the same answer for me. It doesn't matter. So the location is something that I don't, this is not a characteristic of a vector. I do not associate a location for a vector. What I associate with a vector is the slope, is the direction, and the length. So, for example, if I ask you what is vector minus A, instead of to bother yourself to draw this from here, you can simply put the arrow here and say that this is minus A. That's also correct. Because that's the same vector. Parallel here, they are lying on top of each other. They have the same lengths, but one of them is pointing in that direction, the other one is pointing in that direction. So if you say that's also minus A, that's completely okay. So remember, there is no location associated with a vector. Okay, now, of course, there are some remarks that they are very, very trivial that you can see. So, remark, what do you think? There are some common properties between this minus sign and the minus sign we use for numbers. So, you know that for numbers, what happens if I have two negative signs? Minus, minus 2. What's the answer? It's positive 2, which we just simply write 2. Do you think that the same thing happens for this minus sign, which is totally different? Do I have minus a vector? What's your opinion about minus of minus a vector? Does it become, yes?
It's the opposite direction of the opposite direction, right?
Yes?
And it's just positive.
Yeah, it's like equal to itself. So you see, if I ask you, let me clean this blue one. If I ask you to draw the opposite to this arrow, forget about the name. If I ask you to draw the opposite of this arrow, this would be this arrow. The negative of this arrow would be this arrow. If I ask you to draw the negative of this arrow, what it will become the same arrow. Yes? So it is clear that the negative of a vector is the vector itself. Yes? So that's also the same thing that we can have it here. Another thing is that what is negative 0 in numbers? What is negative 0? It is just 0. Do you remember what is the 0 vector? The 0 vector is just a point. There is no direction. So if I have a vector whose initial and final points are the same point, then that vector is called as the 0 vector. For example, if I ask you what is this vector AA,
0.
then that's the 0 vector. Okay? Now, what happens if I negative the 0 vector? Yeah, it's a little bit strange, but that's the 0 vector itself, yes? Because you might say that there is no direction associated with the 0 vector, you're right. But then that's also intuitively clear that this should be the case. But, yes?
But can it be called a vector if it doesn't have a direction?
Yes, that is the only vector without the direction.
Okay.
Yes? Okay, so this is number 1, property number 2. Property number 3. What do you think about the size, the length of vector negative A and the vector A itself? Do you agree that they are the same? So you see, the size of negative A and the size of the A itself, they are exactly the same. Even though one of them is pointing in one direction, the other one is pointing to the other direction. So you need to remember that one as well. So then let me write here. If I have 2 points, any points, A, B, if I consider this vector and if I consider this vector, what is the relation between vector AB and vector BA? So I have 2 points. So for example, I have a point here, another point here. When I talk about vector AB, it means the initial point is A, the final point is B. So if I ask you to draw the vector AB, to construct vector AB, you will draw this one. This one is vector AB. Now I ask you, what is vector BA? It means B is playing the role of the initial one and A is the final one. So you start from here, you put the tip of the arrow here. So this is your vector BA. But what is the relation between these 2 arrows? Yes?
They could be the negative.
They are the negative. So remember, this is a very important fact. So if you have a vector symbol of A and B, if you decide to interchange these 2, you have to put a negative sign there. This is not in geometry, yes? So for example, if I want to name, if I have a triangle, it doesn't matter if I call this side AB, or if I call it side BA, they are completely equivalent. But when we talk about vectors, because there is a direction associated with any vector, it's crucial to differentiate between the initial and final points. So it means that if you write AB vector, if you decide to interchange them, you can do that, but you need to put an extra negative sign there. That's also something that very important. Okay, now let me remind you about addition of 2 vectors again. I hope that you haven't forgotten that, but I will repeat most of it here. So let me addition of vectors So do you remember what I told you? So for example, let me remind you by example. So assume that you have this vector, and then you have another vector which starts from the final point of the first vector. In each case, I want you to construct this vector. Okay? This is the most standard one. Another vector starts exactly from the final point of the another vector, and I want to add them. If this is the case, do you remember what we are supposed to do? You need to connect the initial point of the first vector to the final point of the second vector. And the important thing is that you need to put the tip of the arrow at the final point. This blue vector is called A plus B. Yes? But what happens if the vectors are not exactly drawn in that way? But this is not a big deal, because I told you that the location is not important for the vector. You can just what we call parallel transport the vector so that it is drawn from the tip of the initial vector. So let me, for example, tell you this picture. So what happens if I want to add these two vectors? I have a vector A here, but the second vector has started from the initial point. So assume that I want to add these two vectors drawn for you here. Remember, this is not the standard drawing, yes? The standard drawing for addition is that the second vector, or one of the vectors, it doesn't matter which one, it starts from the final point of the other vector. If that is already the case, then it is very simple. Just connect these 2 points, and remember, you have to put, by definition, to put this tip of the arrow at the final point, not initial point. Okay? But now you see this is not the standard one, yes? Because they start from the same point. So then what we need to do, I need to parallel transport the second vector from the final point of the first vector. What do I mean by parallel transport? It means that I want to transport this vector so that it remains parallel to itself with the same direction and with the same length. Okay, so it means that from the final point of this initial vector, I draw a line which is parallel to this vector, and then I parallel transport it here, something like this. If I call this vector B, I am also allowed to call this vector B because they have the same length, they are parallel, and they are pointing to the same direction. And then I can momentarily forget about this vector. Now this is again the standard situation, yes? So if I want to draw the vector, what I need to do, I need to connect the initial point of the first vector to the final point of the second vector. And then remember, you have to put the tip of the arrow at the final point. So this vector is vector A plus B. Yes? Is that clear? So let me draw one more. So number 3. So what happens if I have this situation? This becomes a little bit harder to draw it precisely, but hopefully you understand what I mean. So I have this vector. So let me draw another vector in this form. I want to add these two vectors. So what I need to do, of course, if you want to, you can just parallel transport 2 vectors somewhere else, so if you're confused. But I think it's not very complicated. So what I do, I take the final point of the first arrow, I parallel transport this, and draw it from the final point here. So what does it mean? It means that from here, I draw a line which is parallel to the second vector, something like this. And what I do, I parallel transport it here. So something like this. So it will be something like this vector. So you can have your ruler to measure the sizes and things, but what I care here is that you need to learn what to do, okay? So hopefully this is a good way of doing that. So I don't need the rest of it. So let me clean it. So if I call this vector B, that's also the vector B. Again, the rule is the same. I connect the initial point of the first one and connect it to the final point of the second one, and I put the tip of the arrow here. So this vector that you see here is called is the vector A plus B. In the exam, if I want to give you this kind of exam, you don't need to have a precise ruler. I will draw them in a gridded paper or whatever, these square vectors. It's very easy to draw. You just need a normal, very simple ruler so that you can draw them precisely. Okay, let me, this is also good to know. For example, what happens if the vectors are already parallel? It doesn't matter if you follow the rule. So for example, assume that you have a vector here, and there is another vector. So let me call this one vector B. I will try to draw this exactly parallel, so you can just do it better with the pen and paper. So let us say this is vector A. Now I want to draw a vector A plus B. Okay? So what should I do? The rule is the same. I need to parallel transport the second one from the final point of the first one. Yes? So what does it mean? It means that I will take this one and put it here. Yes, here. So this becomes the vector B again. And then what you need to do, of course, if I want to draw it carefully, it should be exactly here. I need to connect the initial point of the first one to the final point of the second one. But if you draw it, it becomes exactly on these two. But because I want to show this, let me draw it from here. Yes, so this would be the vector A plus B. Yes? Okay, and let me do one more. Number 5. What happens if I have this situation? I have vector A in this direction. I have vector B parallel to it, but in this direction. Yeah, let me make it parallel. So try to draw it parallel. Okay, so this is vector B. So what should I do if I want to add A to B? I need to do the same thing. I need to take this A, parallel transport, and draw it from the tip of this arrow. So it means that I have to start from here, okay, and draw this vector here. So it becomes this vector. You see, let me change my color. This is the blue one, which I am drawing on it. So it should be the same size if I put it here somewhere, for example. But if you really draw it carefully, it becomes exactly on this black line. But if I draw it in that way, it's not clear. So this is also vector B. Okay, but where is vector A plus B? Every time, don't get confused. The initial point of the first vector is here. The final point of the second vector after being drawn from the tip is here. Okay? So you need to connect them. So just connect them. But where should be the tip of the arrow? It should be at the final point. This one. So this red one that you see is A plus B. Understandable? Yes. So every time I am doing the same thing, if I want to add A to B, I kept A the same. I parallel transport B so that I draw it from the tip of that first arrow. And then I get 2 points. The initial of the first one, the final of the second one. Just connect them and remember that you need to put the arrow at the final point. So that's the only thing that you need to remember. Something is interesting in these pictures. So first of all, if I write something like this, do you understand what I mean? Do you think that this is a correct relation? What is the meaning of this? It tells you the length of A plus B. Yes? This tells you the length of A plus the length of B. First of all, do you think in theory these two plus signs denote the same concept in mathematics or not? Yes or no?
Yes.
Yes or no?
Yes.
Yes.
No. Why? Because this plus is the addition for two vectors. They are arrows. Okay, they are geometric shapes. I want to add two geometric shapes. This is what we learned here. Okay, but what is this one? A is a vector. This is the magnitude of the vector. What is the nature of this quantity here? This is a number. Yes, this is another number. This is the length of vector A. This is the length of vector B. So this addition is addition between two numbers. But this addition is addition between two vectors. I come to you. Okay, this is the addition between two vectors. Is that understandable? So this is I would say an abuse of notation. So this is the way that mathematicians do, but this is not confusing because you need to understand it yourself. Here I am using the same symbol that I am using here, but there's a very big difference between this positive sign here and that positive sign here. This positive sign is adding two arrows together. We didn't know about that. For example, I cannot teach a primary school how to add 2 plus 3, and then after teaching that, I give them two arrows and then said, okay, in the exam, you need to add these two arrows. You understand? They are totally different concepts. Okay, so here, this addition is between two vectors. I have two vectors. I add them. It becomes a new arrow. This means the size of the new arrow. But this means the size of this arrow. This means the size of that arrow. These are two numbers. So this addition is just the normal addition that you learned from primary school, how to add two numbers. Okay? So be careful, first of all, these two things are different. But now, do you think that
No.
So now, Benjamin, you wanted to ask a question or you answered this?
Yes, I wanted to say, but that the thing you wrote would only work if you define a direction first. So in the example 5, it's the same as having the length of A minus the length of B with the direction of B.
Yes, yes.
So you would have to define a direction for the thing to work if the plus
This
sign
one?
would be, if the plus sign would be the same. You would need to define a direction. Was what I was going to say.
No, everything is well defined.
Yes, but I mean on the right side, if the plus would mean the same, you would have to have a direction for the right side's length of B.
No. First of all, if I ask you, is this guy here, the whole package, is it a number or is it an arrow?
It's an arrow.
It's a number. Be careful because you see this symbol.
Oh, yeah.
This means the magnitude of what you see inside. If I ask you what you see inside, you would say this one. Is this an arrow? Is this an arrow or a number? You would say this is an arrow. Yes? This is an arrow. Yes. But as soon as I put this symbol around it, I mean the length of this arrow. Then the length of this arrow is not an arrow, is a number. Yes? So what I have on the left-hand side is a number. Let us analyze what I have on the right-hand side. I have a number again because A itself is an arrow, but the magnitude of an arrow is a number. This is also an arrow, but the magnitude of the number of the magnitude of an arrow is another number. But now I am adding two numbers, it becomes a new number. This claims that the number on the left is equal to the number on the right. this might happen that this claim is true, or might be this claim is false. But based on evidences that you see on the picture, you probably can immediately realize this is not true. Yes? So for example, in this picture, you see the length of this red arrow is even smaller than the blue one itself, let alone that if I add another one to it. Yes? So you see that in general, there is no guarantee that the length of the sum of two vectors is equal to the sum of the lengths of two vectors. But there is a theorem that in any triangle, we haven't studied that before, but this is usually in Persian literature, it's called the Donkey Theorem. And the reason is that probably if you put a donkey here, because in Iran, I don't know, the donkey is the symbol of stupidity or something like that. I don't know. Is there any animal in Sweden like this? Okay, but anyway, I don't know why. So they say that, okay, even the donkey knows if the donkey is here and the food for the donkey is here, the donkey will go straight toward that food, okay? But if it is an insane donkey, it will go in that direction because it is more, it's taking more time. And they say that, okay, when donkey knows about that, let alone about humans, yes? Something like that. But by the way, this is not a proof. We have a proof, but this is not at the level of our lesson, so I just skip that. But this is always the case. If you have a triangle, if you add the sizes of two lengths of those, it is always greater than the third one. It's always the case, okay? So this is why a straight line between 2 points is the shortest path between 2 points, okay? This is the reason. So be careful about this point. Don't take this equality for granted. There is only one case this is true in all these pictures. Can you say which one? For which one of these pictures this equality is true? There is only one picture here that this is true. Number 4. Yes? For example, assume that this is 2 centimeters, this one is 5 centimeters. You see that the red one is 7 centimeters. Only this picture, only these circumstances squares with this equality. Other ones, or in all of them, this is a smaller. So this, let me write this and I will come back to your question. Okay, so let me write this one here for you. Yes. This is very, very important. Don't take these things for granted. Okay, if you want to invent a new rule, you have to have a good reason why this is true. So, remark. Let me write this remark. For any two vectors, A and B, it doesn't matter. You don't need to see the picture to claim this. For any vectors A and B, the size of A plus B is less than, but sometimes equal to the length of the first one plus the length of the second one. Okay, so don't misunderstand that I can write equality. Equality in all these 5 pictures, equality is happening only for this case. So let me, yes?
You forgot to make B a vector.
Oh, thank you. Yeah, thank you. So, and then what I need to write, so then I would say, moreover, the size of A plus B is equal to A normal, the magnitude of A plus the magnitude of B, if and only if. Yes, that was also a part of our discussion. Do you remember I told you that sometimes in math literature you see IFF, meaning if and only if. If and only if. Can you tell me when this happens by that picture? When this happens, if I want to write it in words, if and only if A and B
Has the same direction.
are parallel and pointing to the same direction. Yes, A and B are parallel and pointing to the same direction. Exactly. And there is a famous name for this. This is called the triangle inequality. Inequality. The reason that this is called triangle inequality, because the reason that this one is smaller than this one is being established in a triangle. The sum of the sizes of two sides is always greater than the size of the third one. Yes, Yajol, do you have questions?
Yeah, so in example number 5, if we are to give a number for vector b, for the length of vector b, is it going to be a negative number?
No, the length cannot be negative. I cannot say that the length of a vector is negative.
But it's
The length, no, it doesn't matter. Be careful, that's also a good question. The length is always positive. This doesn't depend in which direction. That's another concept. We will come back to that. That's called a component of a vector. A component of a vector can be negative depending in which direction it will point. But be careful. That's also, I take it for granted. But if that's also your question, be careful. The length of a vector is always a non-negative number. If I have the 0 vector, the length is 0. If the vector is not 0, the length is always greater than 0, regardless of the point that the vector is pointing, because I take my ruler and I measure the size. It cannot be negative, yes? Be careful about that. So this is also good to know. Okay, now let me write another remark for you here. These are the properties of addition of vectors. So let me write remark. These remarks that I write are extremely important. By the way, the notion of vectors is extremely important. Unfortunately, I think this is the only time that you study vectors in high school. This is why I have chosen to teach vectors for math specialization, because it's extremely, extremely important. Then I don't understand how do you want to realize, how do you want to solve physics problems. Sometimes you can solve them just by in an ad hoc manner. But if you want to have a deeper understanding of what's going on, I really want you to learn this. And if you come to math specialization with me, I will continue to a more advanced level. So vectors are a very important tool in the hands of mathematicians to solve some problems, especially in physics. Okay, so let me write this remark. The remark is that, number one, so let me write all of this with black here now. Okay. So the first thing is that there is no difference between A plus B and B plus A. So it doesn't matter if you parallel transport B. So let me motivate you a little bit. So assume that I have this situation. I have A and B. I want to add A to B. So I told you that if you want to add A to B or B to A from this one, so you parallel transport this from here, and then this would be B, and then this vector becomes A plus B. But you see, it doesn't matter if I parallel transport A from the end of this. Yes? And if I connect these 2 points, put the tip of the arrow here, I will get the same vector. So it doesn't matter if I fix A, parallel transport B, and find A plus B, or fix B and parallel transport A and find A plus B. At the end, I will get the same vector. Is that understandable? So it's like numbers. In numbers, it doesn't matter if you add 2 plus 3 or 3 plus 2, yes? So this property is called commutativity. Yes, commutativity, yes? So we can commute them. The answer is the same. Yes?
Is it possible to multiply vectors?
Yes, but that is out of the scope of this, beyond the scope of this list. There are two products. We have three products for vectors. One number multiplied by vector that we had studied, we will study it again. But we have two type of multiplying two vectors together. One of them is called inner product. The other one is called cross product. But these are, I will cover them in math specialization because they are very, very important concepts. Yes.
Now that we're on that subject, will we learn how to subtract or divide the vectors? Or?
The division of vector is completely another story.
Okay, and the subtraction?
No, subtraction we will learn in Math 1C.
Okay.
Yep. So A plus B is equal to B plus A. It's called commutativity. So it means that if I commute these, if I interchange these two, the result is the same. This is some kind of a motivation why this is the case. Yes. Another one is associativity. Associativity. These names you don't need to remember, but I think little by little it's good to know these names. These are not in the book, so you don't need to remember. So associativity tells you that if I have three vectors, it doesn't matter how I prioritize if I want to add them. So for example, if I have three vectors A, B, and C, I want to add them. It doesn't matter if I add these two first and find the vector and add it to the next one, or I add these two vectors first and then add A to it. This is associativity. Let me write all the properties. I will come back. So number one, number two, number three. Of course, this is very trivial for you. What happens if I add the zero vector to a vector? Nothing will happen. So it will give me the same vector. It doesn't matter if I add zero to any vector. The answer is the vector itself. But tell me, what happens if I add a vector to its negative?
Zero vector?
The zero vector, it's very good, yes. You should write the zero vector. You shouldn't write zero because the sum of two vectors is not supposed to be a number, it's supposed to be a vector. And then this becomes minus A plus A. Okay, let me draw a diagram for you to at least motivate you why this should be the case. Okay, so for example, to motivate you about number two, so let me draw three vectors in this form. So let us have this vector A. Let me have this vector B, which is drawn from the tip of this vector. Let me draw another vector C from here. Okay, so assume that I have three vectors. I want to motivate by drawing this picture so that the left-hand side is equal to the right-hand side. Okay. So I have those three vectors. I have intentionally drawn them in a standard way. One of them starts from the tip of the other. Okay, if I want calculate is not a good word because calculate is for numbers. These are arrows. If I want to construct this arrow, what I need to do, which one has the priority? I have two addition operations, this one and that one. But the priority on the left-hand side is given to which one? Which one has the priority, this one or that one? The inside, because of pair of brackets. That is the meaning of pair of brackets. So tell me, what is A plus B? A plus B, I have to connect the initial point of A to the final point of B if the second vector is drawn from the tip of the first vector, which is the case here. So this vector, I had to have my ruler with me here, sorry. Okay, so here, this would be vector A plus B. Okay, now forget about these two vectors. You have a blue arrow and a black arrow. You want to add this blue arrow to this black arrow. But the black arrow has been drawn from the tip of the blue arrow. So it's in the standard form. So if I want to add the blue vector with this black vector, what's the answer? I need to connect the first point to the final point. yes, and put the tip of the arrow here. So this red vector that you see here is a plus b first, and then plus c. Agree? This is the way that I can draw this vector. But now let us go to the right-hand side and try to construct this vector. But which one has the priority? Again, I have two additions here. Which one has the priority? The one in the pair of brackets. So I need to add b and c first. So what should I do? I need to add b and c. Can you tell me which vector is that? I don't have any extra colors, so let me see. Yes, I have it here. So can you tell me what is b plus c? B is this vector. C is this vector. They have been drawn in the standard way, yes? So the initial point of B should be connected to the final point of C, yes? So I will connect this. And where should be the tip of the arrow? It should be at the final point. So if I ask you what is this orange one, you would say this is B plus C. This orange one is B plus C. But now I want to add A to B plus C. You see, I want to add A to B plus C. Forget about the names. I have a black arrow and an orange arrow drawn in the standard form, and I want to add these two arrows together. So what should I do? I need to connect the initial point of A to the final point of B plus C, which will be exactly the same. And where should I put the tip of the arrow? Exactly here. So this dotted line actually represents A plus B plus C. So you see that they actually overlap on each other. So this is one motivation why it doesn't matter if I do it in that way or in that way. So it means that don't worry about pair of brackets at all. You can just throw them away. It doesn't matter in which order you add them. Yes, please.
Now also include C plus B parenthesis A.
Yes. Yes, but there is a delicate point there. If you say this is also C plus A plus B, you are not using associativity, you're also using commutativity. Because what you are doing, you are interchanging two vectors. Okay, if the interchange of two vectors doesn't affect the result, that is not associativity, that's called commutativity, yes? So it means that you are combining associativity with commutativity, you get that rule. But that rule is okay. Yes.
And is it the same thing with B plus in parentheses A plus C?
Yes, exactly. Exactly, that's the same thing.
It's the same thing.
Yeah, it's the same thing, but not only with this one. So you need two properties. You see, associativity, it means that the way that you read the left-hand side and the right-hand side is the same. A, B, C, A, B, C. Okay? But if you write A plus B plus C, and you write it, I don't know, for example, you said B, yes?
Yes.
C plus A. If you ask me, is this equality true? I would say yes. But it involves two properties, not just one property. One property it means that the order of reading shouldn't be changed. You put the pair of brackets and you remove the pair of brackets from one pair and put it for the other pair. But here the order of reading is changed. A, B, C. Here you have B, C, A. They are not the same. So it means that you are using two properties, not just associativity. Commutativity is also involved. So what I want to say, you need to do it in that way. It's a little bit tricky. I don't want to spend time on it. But if you really want to do this, I want to have B outside. So what I do, I use associativity. I put the pair of brackets around these two, for example. Okay, and then I use commutativity to interchange these two. Yes, and then I use associativity to take the pair of brackets around them. Yes, and then I use commutativity to interchange these two.
And it's also the same thing if you remove the brackets on both sides.
Yeah, exactly. So that because of these properties, I am safe to remove the pair of brackets. Okay. Because the role of pair of brackets is to prioritize the operations. If it doesn't matter which one to do, why should I bother to even put pair of brackets around them? But I just want to see, I want you to know that if I want to show this is equal to this, associativity on its own is not enough. I need commutativity to be able to interchange. I need associativity to be able to remove a pair of brackets to put to the other side, yes? So this is one thing that I want to mention. But these are quite advanced things. You don't need to bother about these, okay? So let us go now. I hope that this is also trivial for you, yes? If I add a vector A, this is vector A. Where is vector minus A? Vector minus A is this vector, yes? This is minus A. But if I parallel transport this from the tip of the vector, the final point and the initial point would be the same point. Do you agree? So this is my vector A. Where is my vector minus A? Let me put it here. This is vector A. If I ask you what is vector minus A, you would say this is what vector minus A. I am supposed to connect the initial point of A to the final point of minus A, but they are the same point. So it means that I am connecting a point to itself. So it means that that is the zero vector. So if I add a vector to its negative, it becomes the zero vector. Is that clear? Don't worry about these things. Of course, if you want to be a mathematician, if you want to understand mathematics in a better way, you need to really understand them. But don't worry about for the exam, okay? But just take them for granted. It's better to understand it, of course. Okay, so these are the properties that I want to mention. And I want to give you a rule. This is, I don't know how we pronounce it. He is a French mathematician. I'm sure that it is not Scholz, yes. This is Michel, but Scholz, I think they pronounce it Schall or whatever. Okay.
Yeah, I think
So
it's
Schall. Okay, so that's correct. So this is a very simple rule. Okay. This is a rule, very, very important, but very handy too. So if I ask you add vector AB plus vector BC to give me an answer, you might say that, okay, I can answer you, but I need to draw a picture. Okay, that's good. If you draw a picture for AB, you would say this is, for example, point A, this is point B. I have the vector AB, yes? But then I want to draw another vector, but this point B is the same point B. So it means that I have to start from point B and then go to point C. Whatever it is, you don't need to be worried about. So for example, this is vector, so sorry, this is point C. Now, can you tell me, if I don't give you the names, if I just give you these two arrows and I ask you to add them, what would be the answer? Because is it in a standard form? It is in a standard form, yes, because the second one starts from the tip of the first one. So AB plus BC. What's the answer to this?
ABC.
No, ABC, what's that?
A plus B plus C.
No. Be careful. Forget about these names. I ask you, so you see this name is A, of course. This is B, this is C. But forget about the names. I have two arrows, and I ask you to add these two arrows. What I need to do I need to parallel transport something in this case?
No.
It's already parallel transported, yes? So what I need to do, I need to connect the initial point to the final point. Where should I put the tip of the arrow?
Yes.
On the right-hand side, here in this case. Now let us go back. What was the name here? A. What was the name?
B.
What was the name? C. So if I ask you what is AB plus BC, what's the answer? AC. So that is a very strong rule. You can have it in this way. If I am adding two vectors, if these two names are the same, okay, I don't need to draw any picture. If you draw, it will work, but you don't need to do that. You just in your head eliminate this. What will happen? It becomes AC. This is the Scholz rule. Yes.
If we have AB plus BC plus CD, then
We come to those things. Let us understand this. I will give you examples. Is that clear for everyone? So what I'm saying is that, of course, you can always draw pictures and then try. Sometimes it is inevitable. We have to draw pictures. We should see the picture in front of our eyes to be able to answer. But sometimes, if we are lucky and we have a sequence of these type of vectors, one after the other, with this property, that the letter which is used in between is exactly the same, you can eliminate these two and write the first one first, the last one last, and this would be your answer. You don't need to draw any pictures. Is that clear? Okay. This is called so let me write it here. So Scholz rule is that for any points, it doesn't matter. I have to call them A, B, and C. It's very, very important. We have AB plus BC is equal to AC. And if you want to realize why this is true, you can draw that picture. But let me give you examples. This is a very important example, okay? Without drawing any figures, simplify each item. So simplify each item. Of course, simplify means always as much as possible. Okay, let us do it together. BC plus CD. I write the answer with the blue, okay? Do you think this followed the Scholz rule or not?
Yes.
Yes. Why? Because I have two pairs of a pair of vectors. Coincidentally, this letter that I am using in between is exactly the same. So when this happens, that is the Scholz rule. Yes. So what I can do, in my head, I can eliminate these two, and what is left is B, D vector. If you don't believe, you can draw the picture. The answer would be the same. Yes?
I just want to say, if you give us this question on the exam, how do you know that we're not drawing any figures if we have a scratch paper?
No, you can draw it.
Okay,
It doesn't matter.
Without drawing it.
So whenever, by the way, I really don't care about those questions because what I care is just mathematics knowledge.
Yes.
That's up to you. If you want to cheat, that's up to you. But I will give you another question. So I will tell you, if you just give me the answer, that's not correct. You need to do it step by step.
Okay, and then I'm not allowed to show a drawing as a step.
No.
Okay, so that way I can.
So yeah, but I will never always even think about those questions. Okay, so let me write this one. This is a little bit nice one. AB plus BA. What is this one? The zero vector.
It's ABBA, actually.
Yes. So yeah. Why? You can do it in two different ways. Do you remember what is the relation between BA and AB? Do you remember in the beginning of the lesson today, I told you that if you interchange these two, you can do it, but the price that you need to pay is a negative sign. This is one way of looking at that. So if I ask you what is the relation between BA and AB, you would say that these two vectors are negative of each other. And then you see on the board, if I add a vector to its negative, the answer becomes 0. This is one way of doing that. But another way of doing that, yes?
No, actually.
Yes. So another way to do that, can I use this rule, this Scholz rule for this one as well?
Yes.
Yes, because you see these two are the same. Yes, so I can eliminate this. What is left? A and A. But I told you that whenever you have a vector whose initial and final points are the same, there is a name for that. What's that vector?
Zero vector.
The zero vector. So you have to stop here because I told you that simplify it as much as possible. Okay, so let me write number 3. So what about this one? If I have BA plus AB, of course you immediately can answer, but let us use this rule. What is the answer? Can I use the Scholz rule here as well?
Yes.
Yes, but this time A's are the same. A's are cancelled. What is left?
Zero vector.
BB, which is again the zero vector. So the answer to this is BB, but that is 0. And the answer to this one is AA, but that's 0. If you stop here, that's not complete. If you stop here, that's not complete. You have to give me the zero vector as the answer. Okay, let me go to Casual's actually question. So now we have this. Number 4. I want to teach you a little bit more and then I will stop. So number 4, what happens if I have AB? Let me write all of them and come back to you. You can start with me. AB plus BC plus CD. Let me write all of this in black. Number 5, BC plus CA plus AB. Number 6, AB plus AC plus BC plus CA plus BA plus C. And finally 7, BE plus AD plus EA plus CD. Okay. Okay, could you finish it? Yeah. It's not that hard, okay? Of course, if the pattern, you cannot see the pattern, I am not saying that always the pattern is there. Sometimes it is not possible. We have to refer to the picture. But sometimes if you can see the pattern immediately, it's much easier instead of drawing the picture, okay? So now, do you see the pattern here? You can interpret it in 2 ways. You can take these 2 things first because of associativity and then find the answer, find it with that one. Or if you want, you can take these 2. It doesn't matter. But I don't want you to do it quickly in the exam. Write it in 2 steps. You can do it in your head quickly. That's good. But when I want you to do it in exam, you can say that I take these 2 first. Is it this shall rule or not? I would say yes, because B and B are the same, so I can cancel it. What is left for me is AC. So this AC that you see here is sitting instead of the whole expression here. This is AC. Yes? And then after that, I have plus CD. Can I continue even more? Yes. Because there is another shall pattern, yes? So what I can do, I can eliminate this C, and what I should write? A, D. So you see, without referring to any pictures, you can immediately realize if you draw that picture, the answer would be AD. Okay? So what about this one? Yes? The 0 vector, yes? Because B, C, and C are cancelled. It is BA plus AB. Then A is cancelled. It is BB. And then this is the 0 vector. Yes? So what about this one? Can I use the shall rule here? Partially. No. The answer is no. An emphatic no, okay?
BCAC though.
No, here. Just here, between these 2. That's what I'm saying. What I'm saying is that you see A is in common, but it is very important the common letter is in between. It's very important. You cannot say, if you think, if I give you this, by the way, might be I was a little bit in a hurry. If I ask you, can I use the shall rule to simplify that? And you say that I eliminate A and I write B, C, that is wrong. Because it is important that you have a letter in common, and the common letter should be in between. Then you're allowed to eliminate that, okay? So be careful, don't be in hurry. Okay, so here I cannot use this, but can I reorganize it in a way that I can use it effectively? The answer is yes, okay? So for example, which one do you take with together? So here, for example, I can take this AB and I can take this BC, you see AB plus BC, and then I have another CB at the end. So you see, I took this one and this one and this, and this one together in one package. And then what I have AC and CA. I can put them in one package. There is one more left, and that is BA. I am not saying that this is the only way. You might have found another way for yourself. But that is one way that this method will work. So be careful. AB, AB, BC, BC, yes, CB, C. That's good. AC and CA, AC and CA. And finally, one is left, which is BA. Do you agree? This is one way, of course. But now, can you tell me what is the answer of the first package? You can do it in your head now. You see, B and B are the same, so it becomes AC. And then CB, AC and CB is AB. Plus, what is this one? This is AA. Let me just write it for the time being. And then I have another one, BA. But let us continue. What is this one, as you said? It is 0, so it doesn't matter. It becomes AB plus BA. But what is this one again? 0. This is 0 because this becomes AA, and AA is 0 again. So you see, without drawing any picture, just by algebraic calculation. Yes?
You can just eliminate all the terms directly because AB.
Because AB, exactly, and BA are opposite.
Yeah.
Exactly. AC and C, BC and C. If that's also correct. Yeah. Here, what do you think here? What do you think here? Is there any way that I can do it here? Yes, because you see, let me write it BE. Is there something starting with E? Yes. So let me write it here. Is there something starting with A? The answer is yes. But then I also have CB. If I realize that if I put CB here, that's okay. You see, I put CB first, and then I put BE, then I put EA, then I put AD. Yes? Now everything can be collapsed into one single term, yes? Because B and B are the middle letters, they are the same. I can cancel, it becomes CE. E and E are the same, it becomes CA. A and A are the same, it becomes C. Bye-bye.
Wait, what? Shall we go?